Hi, this is Dr. Chandran. Today's topic is collapse load. We know MP is nothing but Fi into ZP. MP is nothing but plastic moment. The load which gives plastic moment is called the collapse load. From the collapse load, we can calculate working load. Working load equal to tau is divided by load factor. So during collapse load, the structure becomes unstable. What is unstable? Unstable means number of equilibrium equations are greater than number of reactions. So once the structure becomes unstable means the mechanism will be formed. So during an unstable condition, the deformation will keep on increasing. Consider a simply supported beam. It is subjected to point load at the center. Initially, there are two unknowns RE and RB, two available equations MZ and Fi. Two equal to the structure is called stable and also determinate. If you have increased the load W, what will happen? One more hinge developed at center. Now available equations are 3. 3 number of unknowns are 2. 3 greater than 2. So this structure is unstable. Unstable means automatically the mechanism will be formed like this. So the hinge will be developed at the center. So the unstable, this is called the mechanism. So likewise, if we consider the fixed beam subjected to point load at center, initially four unknowns, two equilibrium equations. So summation of M is equal to 0, summation of F equal to 0. Summation of H is neglected because there is no horizontal forces. So two equilibrium equations, four unknowns. The structure is called stable, indeterminate. If you increase the load, two hinges will be developed first at the ends. So now how many equations are available? Initially 2, now 2 hinges means totally 4 unknown, 4 equilibrium equation, 4 unknowns. So the structure is becomes stable. Now the structure is determinate. Again increase the load, what will happen? One more hinge developed at the center. So now available equations are 5, unknowns are 4. So this condition, so available equations are greater than the unknown reaction. The structure is becomes unstable. During unstable condition, the mechanism is formed like this. So likewise, the possible mechanism can take place. Number of mechanism n equal to n minus r. N is nothing but possible plastic hinges. R equal to degree of redundancy. Here, there are three theorems: static theorem, kinematic theorem, and uniqueness theorems are used to find out the collapse load. First, static theorem. For a given structure and loading, if there exists a bending moment distribution which is safe and statically admissible with a set of loads W, then W less than or equal to WC. Here, the calculated load W less than or equal to WC. Consider a simply supported beam subjected to point load at center. Due to point load, the moment is M, will be developed at center. M equal to WL by 4, you know that. This moment always less than plastic moment MP. This is called safe. The bending moment distribution which is in safe. Then the load W always satisfies these two equations. Summation of Fi equal to 0, summation of MS equal to 0. So statically admissible. So from these two conditions, the calculated load W always less than or equal to WC. This theorem is called a static theorem or lower bound theorem. Now kinematic theorem. For a given structure subjected to a set of load W, the value of W found corresponding to any assumed mechanism must be either greater or equal to the collapse load. That is, here the W greater than or equal to WC. So the value of load W always calculated from the mechanism. The last one is uniqueness theorem. So uniqueness theorem is nothing but the load W which is equal to WC. The statement is, if we obtain a bending moment distribution satisfying static theorem, and in this distribution the bending moment is equal to the plastic moment at sufficient sections to form a mechanism, then that load is equal to collapse load. That is W equal to WC. In the static theorem, W less than equal to WC. Kinematic theorem, W greater than WC. But in the uniqueness theorem, W equal to WC. Okay. Now, two methods are used. That is static method and another one is kinematic method to find out the collapse load. First, we are going to see static method. So, the static method fully used bending moment diagrams. So consider simply supported beam, the load is acting at center, the bending moment at center we know the tau L by 4. So the maximum, the hinge is developed means the moment is MP. So MP equal to tau L by 4, from the tau is equal to 4 MP by L. From that we can calculate tau is tau by static method. Now coming to second example, in this fixed beam subjected to point load at center, we are going to find out the plastic collapse load. So first we have to draw the bending moment diagram. For fixed end supports, the bending moment is rectangle. The moment value is MP. At center, this value is we know that this value is tau L by 4 due to pre-bending moment diagram. This is tau L by 4. Now here this height is MP already we know. This also MP due to the additional load. This also MP. So MP plus MP is equal to tau L by 4, total height tau L by 4. Tau is equal to 8 MP by L. Like that, the collapse load WC for the fixed beam subject to point load is 8 MP by L is calculated. So similarly, in the third example, considering a property cantilever. In the third example, consider a property cantilever subjected to point load W at A distance from left support, B distance from right support. If you draw the bending moment diagram for the load, it is a triangle. The height is tau AB by L. For the fixed moment, for the fixed condition, the moment is MP at center, 0 at the right hand side. So this is the bending moment diagram for the given loading. So initially, if you apply the load, the plastic hinges will be developed at the edge, that is MP, this height MP. Second plastic will be developed at this under the point load from this point. So if you calculate the MP value, this value is equal to MP by L. This MP total divided by L equal to this distance I am assuming this is x by this height is I am taking it as x. This distance is B. You know, this distance is B, x by B. So x equal to PL B by L into MP. So this MP plus this MP. So this one is P by L into MP plus this height. This height is also MP. So if you add both, you will get the total height. Total height is tau L by H. So rearrange that tau is equal to MP into L plus B by A plus B. This is the collapse load for this condition. Now, coming to kinematic theorem, this theorem always using virtual earth principle. In this principle, the system of forces are in equilibrium in a given virtual displacement. That means the work done due to external load equal to work done due to internal forces. Okay. Here, consider a simple subjected to load W at center. External work done is nothing but load into displacement, delta, WC into delta. Internal work done is nothing but how many moments, plastic moments are developed. In the center only the plastic moment into rotation. So external moment is nothing but external work done equal to WC into delta. Internal work done is nothing but MP into theta. So equating these two, we will get the WC. This is nothing but this is a virtual work principle. So internal work done for this case is MP into 2 theta. Here theta, this theta plus theta, 2 theta. External work done equal to load into displacement W into delta. So how the delta is calculated? Theta equal to opposite side by L by 2. So delta equal to L theta by 2. Substitute in this case, we can get the W is equal to 4 MP by L. So total external work done for this case, for the second case, is simply supported as a fixed beam subjected to point load at the center. Total external tau into delta. That is delta can be rearranged like this, tau L theta by 2, L theta equal to L theta by 2. Total internal work done is nothing but here the plastic hinges are number of hinges 1, 2, 3 hinges. So MP into theta, MP into theta, MP into 2 theta. So MP into 2 theta. So for equating both, we will get W is equal to 8 MP by theta. Like that, another example. Fixed beam subjected to UDL throughout this span. Total internal work done is nothing but how many internal hinges? 1, 2, 3 hinges. MP theta plus 2 MP theta plus MP theta. But coming to the external work done equal to total load into average displacement. Total load into average displacement. Displacement center W. Total work done is nothing but total load equal to tau into L is the total load. into delta by 2 tau L by 2 into the delta can be written as L theta by 2. That's therefore tau L square by theta by 4. So equating these two external and internal, we can get the collapse load tau is equal to 16 MPa by L. Now the last case, consider yes property candle subject to W. So the mechanism is formed like this. At center one mechanism MP, at the left support one MP, so MP into theta 1, here theta 2 because unequal distance, theta 1 plus theta 2 at center. So total internal work equal to MP into theta 1 plus MP into theta 1 plus theta 2. Theta 1, theta 2 are calculated by using that. Theta 1 equal to delta by A, theta 2 equal to delta by B. So substituting these values, we can rearrange like this: MP theta 1 plus MP theta 1 plus A B by B theta 1. So like that we can write. So MP theta 1 equal to L plus B by B. So external work is nothing but tau into delta. Tau into delta. Delta can be written as A theta 1. A theta 1. Delta is nothing but A theta 1 or B theta 2. We can write like this. So MP theta 1 L plus B by B equal to tau A B A theta 1. Therefore tau is equal to MP L plus B by A B. This is the collapse load for this condition. Like that we can calculate the collapse load for other examples. We will see some more examples in the next class.